let's link the net change theorem to an old friend that we'll see what happens as we go along. So here's the net change theorem, and let's remind ourselves that little f here is the rate of change of big F. If I wanted to write this in terms of little f, I'd just kind of change all the names. We can change names in math, right? I'll just switch everything from big F to little f and integral a to b, but now I can't switch little f to little f. I need to write whatever the rate of change of this function is. So I could say, well, what's the rate of change of little f? That's just little f prime dx. Since little f prime is the rate of change of little f, so far it seems like I'm just playing with symbols, but do we remember anything else from the whole semester where we said this equals that plus something? And here's something slightly complicated. Do you remember any other formula from the whole semester, maybe way back in chapter 2, where we said this equals some base value plus something about the difference between those two things? Well, that was our tangent line, right? So tangent line, which we also call the best local linear approximation. We wrote that as L of x equals f of c plus f prime at c times x minus c. And again, in the spirit of just playing with symbols, we were saying kind of anchoring at c and going to x, but in this net change theorem, we're kind of anchoring at a and going to b. So we could replace x with b and say, instead of anchoring at c, we're anchoring at a. Let's change that. X became b and c became a. So now is the link between those two a little more clear, and let's think about the link between integral a to b of f prime and f prime at a times b minus a. So what's the link between integral a to b f prime of x dx and f prime of a times b minus a? Well, let's remember that for our tangent line, we're using a constant slope. We're using the slope at our anchor point to predict out into the future. So what if, so let's write that down. So for a line, the slope is constant. So we're using f prime at a, and that's our slope m. What if f prime itself, so our tangent line has a constant slope. What if our function itself had a constant slope? That f prime was just equal to m everywhere. Then the integral a to b f prime of x dx will be the integral a to b of m dx, because we're saying if our function had a constant slope, f prime would just always be some constant. We're calling it m. And what's the integral from a to b of m dx? Well, you could say that's m times x on our bracket a to b, which is m times b minus m times a, or you could write that as m times b minus a. Where have we seen m times b minus a before? Right here, slope times b minus a. So if our function had a constant slope, if our function was linear, then we would get exactly this tangent line out of the net change theorem. So then the net change theorem formula is the tangent line formula. Now, you're probably saying, well, that's great if f is linear, but if f is linear, I don't need calculus. I can do just fine with algebra, and that's true. So let's go back and think about what if f is nonlinear. Well, what's one of the big ideas of calculus to deal with nonlinear functions? Zoom in enough until they look linear. So let me draw a big curve here. And we'll have our anchor point here is A. And we'll have a tangent line. So this is our function f. This is L of x. And it has a slope. Slope like that, which is f prime of A. And then we're saying, so L is a linear approximation. It's what you get if you pretend that f has a constant slope over here. If I pretend that it has a constant slope, but I don't follow it all the way out here, I just follow it out to here, I get this approximation. And I could say maybe this is a width like dx or delta x. And then what the integral formula is doing is it's saying, okay, now use the new slope at that value, and use that new slope to come out here, and that's another width dx, and then start there and follow the new slope. So we're constantly updating the slope. You could argue whether you should kind of go up to the curve each time and then project out the new slope, or just start it from there. If we're actually adding up these distance times new slope, it seems like we should be kind of starting from the old place, not moving up, because how would we know how far to move up? But what this net change formula is basically doing is it's saying current slope times dx plus another slightly updated slope times a new dx, same value dx as before, but another step over. So the net change formula is basically a continuously updating tangent line. It's using tangent line approximations over and over. So we can say, except with the integral, the dx value is infinitely narrow. Or you could say it's infinitesimal. So the net change theorem is adding up a whole bunch of tangent line type changes. And when we say a whole bunch, we mean an infinite number of them, just to get from one place to another, all these infinitely narrow boxes. So how's that for coming full circle from derivatives and tangent lines all the way to integrals and back?